Beneath the dim glow of a faint red star 48 light-years away, a rocky world named LHS 1140b is quietly exhaling its atmosphere, literally. Helium, the lightest element, is seeping into the void, a faint but unmistakable whisper that this distant planet has a sky. For billions of years, it may have clung to this fragile envelope, untouched by the solar winds of its host star. Now, astronomers have detected this rare leakage, the first confirmed atmosphere on a rocky world in a habitable zone. It's a discovery that blurs the line between exoplanet and Earth, raising the question, could this alien world hold secrets of life itself? Astronomers have made a groundbreaking discovery, the first confirmed atmosphere around a rocky planet in the habitable zone of another star. This finding, announced in 2026, marks a pivotal moment in the search for potentially life-supporting worlds beyond our solar system. The planet in question, LHS 1140b, is located 48 light-years from Earth, orbiting a faint red dwarf star in the constellation Cetus. What makes this discovery extraordinary is not just the presence of an atmosphere, but the fact that this atmosphere exists on a rocky world similar in composition to Earth, located within the habitable zone, where conditions could allow liquid water to exist on its surface. This revelation opens new possibilities for understanding how planets form, evolve, and whether they might harbor the ingredients necessary for life. To grasp the significance of this finding, we need to start with the basics of what an atmosphere is and why it matters. An atmosphere is a layer of gases surrounding a planet, held in place by gravity. It plays a critical role in regulating temperature, protecting the surface from harmful radiation, and, in some cases, enabling the presence of liquid water, a key ingredient for life as we know it. For decades, scientists have searched for atmospheres around exoplanets, planets outside our solar system, but most of these efforts have focused on gas giants, like Jupiter or Saturn, which are much larger and easier to detect. Rocky planets, which are more Earth-like in size and composition, are harder to study because they are smaller and their atmospheres are fainter. Until now, no confirmed atmosphere had been detected on a rocky world in the habitable zone of another star. The discovery of LHS 1140b's atmosphere was made possible by a unique method, tracking the slow leakage of helium into space. Helium is a noble gas, meaning it doesn't react with other elements, and it's one of the lightest elements in the universe. Because of its low mass, helium can escape a planet's atmosphere more easily than heavier gases like nitrogen or oxygen. However, this process takes billions of years, which means that if helium is still detectable today, it suggests the planet has retained its atmosphere for an extremely long time. By analyzing the faint glow of starlight passing through LHS 1140b's atmosphere, astronomers were able to detect the presence of helium. This method, known as transmission spectroscopy, involves measuring how light from the star is filtered through the planet's atmosphere, revealing the chemical fingerprints of gases present. LHS 1140b itself is a fascinating world. It is about 6.6 times the size of Earth, which places it in the category of super-Earths, planets that are larger than Earth but smaller than gas giants. Its host star, LHS 1140, is a red dwarf, a type of star that is smaller, cooler, and less luminous than the Sun. Red dwarfs are the most common type of star in the galaxy, and their planets often orbit much closer to their stars than Earth does to the Sun. Despite this, LHS 1140b's orbit is just right to place it within the habitable zone, a region where temperatures could allow liquid water to exist on the planet's surface. This is a crucial factor because liquid water is essential for the chemical processes that sustain life as we know it. However, the habitable zone around a red dwarf is much narrower and closer to the star than around a Sun-like star, which means the planet's climate and atmospheric conditions could be quite different from Earth's. The presence of an atmosphere on LHS 1140b is particularly intriguing because it suggests the planet has not only survived the harsh conditions of its star system but has also maintained a stable environment over billions of years. Red dwarfs are known for their intense stellar activity, including flares and strong magnetic fields, which can strip away planetary atmospheres over time. The fact that LHS 1140b has retained its atmosphere implies that it has a robust magnetic field or other protective mechanisms that shield it from these destructive forces. This resilience is a key indicator of the planet's potential to support life, as a stable atmosphere is essential for maintaining the conditions necessary for liquid water and complex chemistry. But how did scientists determine that this planet has an atmosphere? The answer lies in the way light interacts with gases. When a planet passes in front of its host star, a phenomenon called a transit, a small fraction of the star's light passes through the planet's atmosphere. This light is filtered by the gases in the atmosphere, causing specific wavelengths to be absorbed or scattered. By analyzing these subtle changes in the starlight, astronomers can identify the presence of various gases. In the case of LHS 1140b, the detection of helium was a critical clue. Helium is a rare gas in planetary atmospheres, and its presence suggests that the planet has a unique composition. However, the method used to detect it, tracking its slow escape into space, also provided insight into the planet's atmospheric dynamics. This technique, which involves measuring the planet's gravitational pull on the helium, allowed scientists to estimate how long the atmosphere has been present and how it might be evolving over time. The implications of this discovery extend far beyond LHS 1140b itself. For years, the search for habitable exoplanets has been limited by the difficulty of detecting atmospheres on rocky worlds. This finding demonstrates that it is possible to study the atmospheres of such planets, even in the challenging environments around red dwarfs. This opens the door to future missions and observations that could reveal more about the composition, structure, and potential habitability of other rocky planets in the habitable zone. For example, if future observations can detect oxygen, methane, or other gases associated with life, it could provide direct evidence of biological activity on these distant worlds. However, the presence of an atmosphere alone does not confirm the existence of life, it simply means that the planet has the potential to support it. Another important aspect of this discovery is its role in understanding planetary evolution. The fact that LHS 1140b has retained its atmosphere for billions of years suggests that it has a history of stability and resilience. This is significant because planetary atmospheres are dynamic systems that can change over time due to factors like volcanic activity, tectonic movement, and interactions with the host star. The ability of LHS 1140b to maintain its atmosphere despite the challenges of its star system provides valuable insights into the long-term habitability of exoplanets. It also raises questions about the processes that govern atmospheric retention, which could help scientists better model the climates of other planets and even Earth itself. Looking ahead, this discovery represents a major step forward in the search for life beyond our solar system. While LHS 1140b is not yet a confirmed candidate for hosting life, it is a prime target for further study. Future observations using more advanced telescopes, such as the James Webb Space Telescope or the upcoming Extremely Large Telescope, could provide more detailed information about its atmosphere and surface conditions. These instruments would allow scientists to analyze the chemical composition of the atmosphere in greater depth, potentially revealing the presence of gases that could indicate biological activity. Additionally, missions to explore the habitable zones of other red dwarfs could build on this discovery, expanding our understanding of how planets form and evolve in different stellar environments. In conclusion, the detection of an atmosphere on LHS 1140b is a milestone in the quest to find planets that could support life. It demonstrates that rocky worlds in the habitable zone are not just possible but can also retain the atmospheric conditions necessary for life to exist. This finding challenges previous assumptions about the rarity of such planets and highlights the importance of continued exploration. As we refine our methods for detecting and analyzing exoplanet atmospheres, we move closer to answering one of the most profound questions in science: are we alone in the universe? The journey to find out is only just beginning, and discoveries like this one bring us one step closer to understanding our place in the cosmos. Astronomers have found the first confirmed atmosphere around a rocky planet in another star's habitable zone. The planet, LHS 1140b, revealed its atmosphere through helium slowly leaking into space. Located 48 light-years away, the world may have preserved its atmosphere for billions of years, making it a promising target in the search for potentially habitable planets. This part of our deep dive into Astronomers Find the First Atmosphere on a Rocky World in the Habitable Zone focuses on, walk through how scientists found or confirmed this: instruments, telescopes, missions, method, timeline. Make the process itself feel impressive. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. For viewers who want to go deeper than this summary, the primary source linked in the description lays out the full technical picture. Findings like this rarely stand alone, they get compared against earlier observations to make sure the pattern holds up under scrutiny. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. Astronomers have found the first confirmed atmosphere around a rocky planet in another star's habitable zone. The planet, LHS 1140b, revealed its atmosphere through helium slowly leaking into space. Located 48 light-years away, the world may have preserved its atmosphere for billions of years, making it a promising target in the search for potentially habitable planets. This part of our deep dive into Astronomers Find the First Atmosphere on a Rocky World in the Habitable Zone focuses on, go deeper into the underlying science/physics/astronomy that makes this significant. Explain why it matters to our understanding of the universe, in accessible plain language. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. For viewers who want to go deeper than this summary, the primary source linked in the description lays out the full technical picture. Findings like this rarely stand alone, they get compared against earlier observations to make sure the pattern holds up under scrutiny. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. For decades, the search for life beyond Earth has been guided by a single, tantalizing question: are we alone? The answer, however, has always been hidden behind the vast, uncharted darkness of space. Until recently, our understanding of planets beyond our solar system was limited to distant, dim points of light, mere dots in the night sky. But over the past few decades, a quiet revolution has unfolded in astronomy, transforming these distant worlds from abstract possibilities into tangible targets for discovery. Today, we stand at the edge of a new era, where the first confirmed atmosphere on a rocky planet in the habitable zone of another star has been detected. To understand how we arrived here, we must trace the winding path of human curiosity, from the first hints of exoplanets to the breakthroughs that made this discovery possible. The story begins in the early 1990s, when astronomers first began to realize that planets might exist around other stars. Before this, the idea of exoplanets was little more than science fiction. The first confirmed discovery came in 1995, when Michel Mayor and Didier Queloz announced the existence of 51 Pegasi b, a gas giant orbiting a sun-like star just 50 light-years away. This was a watershed moment, proving that planets could exist in systems beyond our own. But these early discoveries were limited to massive, gas-rich worlds, hot, bloated giants that would likely never host life as we know it. The search for smaller, Earth-like planets remained elusive, buried beneath the noise of stellar light and the limitations of early detection methods. The next major leap came in the 2000s, as astronomers developed more sophisticated techniques to detect planets that might resemble Earth. The transit method, which involves measuring the slight dimming of a star's light as a planet passes in front of it, became a cornerstone of exoplanet research. This method allowed scientists to identify planets of varying sizes, including rocky worlds. Meanwhile, the radial velocity technique, which detects the gravitational wobble of a star caused by an orbiting planet, helped refine estimates of planetary mass. Together, these methods revealed a growing catalog of exoplanets, many of which occupied the so-called habitable zone, the region around a star where temperatures could allow liquid water to exist on a planet's surface. This zone, often referred to as the Goldilocks zone, became a focal point for the search for potentially life-supporting worlds. Yet, even as the number of exoplanets grew, the question of whether these worlds could actually support life remained unanswered. Without direct observations of their atmospheres, scientists could only speculate about their potential to harbor life. The challenge lay in the sheer distance of these planets, which made it nearly impossible to study them in detail. For years, the only way to gather information about exoplanet atmospheres was through indirect methods, such as analyzing the light from a star as it passed through a planet's atmosphere during a transit. This technique, known as transmission spectroscopy, allowed scientists to detect the presence of certain gases, like water vapor or carbon dioxide, by observing how they absorbed specific wavelengths of light. However, these early efforts were limited by the sensitivity of ground-based telescopes and the faint signals they could capture. The turning point came with the launch of the Hubble Space Telescope in 1990, which provided a new vantage point for observing distant worlds. Hubble's ability to capture high-resolution images and spectra of exoplanet atmospheres laid the groundwork for future discoveries. In the early 2000s, astronomers used Hubble to study the atmosphere of HD 209458b, a gas giant orbiting a star 150 light-years away. This was the first confirmed detection of an exoplanet's atmosphere, revealing the presence of water vapor and other molecules. While this was a monumental achievement, it still involved a planet far too hot and massive to support life as we know it. The search for smaller, rocky planets in the habitable zone continued, driven by the tantalizing possibility that such worlds might harbor conditions suitable for life. The breakthrough that brought us closer to this moment came with the development of the James Webb Space Telescope, JWST, launched in 2021. JWST's advanced instruments, including its powerful spectrographs and infrared sensors, allowed astronomers to peer deeper into the atmospheres of exoplanets than ever before. Unlike previous telescopes, JWST could detect fainter signals and analyze the chemical fingerprints of distant worlds with unprecedented precision. This capability was crucial for identifying the subtle signatures of atmospheres around rocky planets, which are much smaller and less massive than gas giants. The technology behind JWST also built on decades of advancements in spectroscopy, a field that has its roots in the 19th century but has evolved dramatically with the advent of space-based observatories. As the search for habitable exoplanets intensified, scientists began to focus on planets that not only occupied the habitable zone but also showed signs of atmospheric retention. A planet's ability to maintain an atmosphere is critical for sustaining liquid water and, potentially, life. However, detecting such atmospheres has always been a challenge. Most of the early exoplanet discoveries focused on gas giants, which are easier to study because their large size and strong gravity make it easier to detect atmospheric features. Rocky planets, on the other hand, are smaller and more elusive, requiring more sensitive instruments and innovative techniques to study their atmospheres. The detection of an atmosphere on a rocky world in the habitable zone represents a major leap forward, as it suggests that such planets may have the conditions necessary to support life. The journey to this discovery was also shaped by the evolution of our understanding of planetary atmospheres themselves. For centuries, scientists have studied Earth's atmosphere to understand how it sustains life, but the question of whether other worlds could have similar conditions was largely theoretical. The discovery of exoplanets in the habitable zone sparked a renewed interest in the factors that determine a planet's ability to retain an atmosphere. These factors include a planet's mass, its distance from its star, and the presence of a magnetic field, which can protect a planet from the erosive effects of stellar winds. Over time, these insights have guided the search for planets that might have atmospheres capable of supporting life, leading to the identification of candidates like LHS 1140b. LHS 1140b, the planet at the heart of this discovery, has been a subject of interest for years. Located 48 light-years away, it orbits a red dwarf star and is slightly larger than Earth, making it a rocky world with the potential to support liquid water. However, its atmosphere remained a mystery until recent advances in observational technology allowed scientists to detect its presence. The key to this discovery lay in the planet's unique characteristics, its ability to retain an atmosphere over billions of years, and the subtle clues left by the gradual leakage of helium into space. Helium, a noble gas, is not typically found in planetary atmospheres, but its presence in LHS 1140b's atmosphere suggests that the planet has a stable atmospheric composition that has persisted for an extended period. This longevity is a critical indicator, as it implies that the planet may have the conditions necessary to sustain a habitable environment. The detection of LHS 1140b's atmosphere is not just a triumph of technology but also a testament to the perseverance of astronomers who have spent decades refining their methods. It is the culmination of a long and winding path, from the first exoplanet discoveries to the development of instruments capable of analyzing the faintest signals from distant worlds. Each step along the way has brought us closer to understanding the potential for life beyond Earth, and this discovery marks a significant milestone in that journey. As we look to the future, the search for habitable worlds continues, driven by the same curiosity that has propelled humanity to explore the cosmos since the dawn of time. Astronomers have found the first confirmed atmosphere around a rocky planet in another star's habitable zone. The planet, LHS 1140b, revealed its atmosphere through helium slowly leaking into space. Located 48 light-years away, the world may have preserved its atmosphere for billions of years, making it a promising target in the search for potentially habitable planets. This part of our deep dive into Astronomers Find the First Atmosphere on a Rocky World in the Habitable Zone focuses on explore the open questions, scientific debate, and things that remain genuinely unresolved or mysterious. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. For viewers who want to go deeper than this summary, the primary source linked in the description lays out the full technical picture. Findings like this rarely stand alone, they get compared against earlier observations to make sure the pattern holds up under scrutiny. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. Astronomers have found the first confirmed atmosphere around a rocky planet in another star's habitable zone. The planet, LHS 1140b, revealed its atmosphere through helium slowly leaking into space. Located 48 light-years away, the world may have preserved its atmosphere for billions of years, making it a promising target in the search for potentially habitable planets. This part of our deep dive into Astronomers Find the First Atmosphere on a Rocky World in the Habitable Zone focuses on explain what's coming next, future missions, instruments, or observations that could confirm, extend, or challenge what we know so far. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. For viewers who want to go deeper than this summary, the primary source linked in the description lays out the full technical picture. Findings like this rarely stand alone, they get compared against earlier observations to make sure the pattern holds up under scrutiny. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. In this chapter, we're peering into a discovery that redefines what we thought possible. Astronomers have confirmed the first atmosphere around a rocky planet in another star's habitable zone, a milestone that brings us closer to finding worlds where life might exist. The planet, LHS 1140b, is 48 light-years away, orbiting a dim red dwarf star. What makes this find extraordinary is how they detected the atmosphere, by observing helium slowly escaping into space. This isn't just any atmosphere, it's a sign that the planet may have held onto its air for billions of years, offering a rare glimpse into the potential for long-term habitability. But how did they spot it? Let's break it down. When we think of atmospheres, we often imagine thick layers of gases like nitrogen or oxygen, but LHS 1140b's atmosphere is different. It's thin, and its presence was revealed through a subtle clue: helium. As the planet's gravity struggles to hold onto its atmosphere, helium leaks out, creating a faint signal that telescopes can detect. This method, called atmospheric leakage analysis, is a breakthrough because it allows us to study planets even when their atmospheres are sparse. It's like listening to a whisper across the cosmos, picking up traces of a world we've never visited. Now, why is this planet so special? It's in the habitable zone, the region around a star where temperatures could allow liquid water to exist on a planet's surface. But here's the twist: LHS 1140b is rocky, not gaseous. This means it's a terrestrial world, similar to Earth in composition, but with a different atmospheric makeup. The fact that it's retained its atmosphere for billions of years suggests it's stable, which is a big deal. Most exoplanets we've studied so far have either no atmosphere or one that's been stripped away by intense stellar radiation. This planet's survival of such conditions makes it a prime candidate for further study. But what does this mean for the search for life? Well, an atmosphere is a key indicator of a planet's potential to support life. While we don't yet know what gases are in LHS 1140b's atmosphere, the presence of any biosignatures, like oxygen, methane, or water vapor, could signal processes driven by life. However, the planet's star is a red dwarf, which can be volatile, emitting flares that might strip away atmospheres. Yet LHS 1140b seems to have weathered this, hinting at resilience. This resilience, combined with its location in the habitable zone, makes it a tantalizing target for future missions. This discovery also underscores the power of modern astronomy. By studying how helium escapes, scientists are developing new tools to probe exoplanets in ways we've never done before. It's a reminder that the universe is full of surprises, and sometimes the answers lie in the faintest signals. But this isn't just about LHS 1140b. It's about the broader quest to understand if we're alone. Every confirmed atmosphere brings us one step closer to answering that question. So, what's next? Researchers will continue to analyze LHS 1140b's atmosphere, looking for more clues. Future telescopes, like the James Webb Space Telescope, may provide deeper insights into its composition. But for now, this find is a beacon of hope. It shows that even in the vastness of space, we can find worlds that defy expectations. And that's what makes science so thrilling. Each discovery opens new doors, inviting us to ask bigger questions. If you've enjoyed this deep dive, consider subscribing to FactVerse for daily explorations of the cosmos. Whether you're a space enthusiast or just curious about the universe, there's always more to learn. And if you have theories or questions about LHS 1140b or any other cosmic mystery, drop them in the comments. After all, the greatest discoveries often begin with a single question. Let's keep exploring, together.